That brings us on to cryptography. We actually use not so much cryptography. Maybe that's not quite true. We don't use as much cryptography, or at least we don't have as many cryptographic keys as with Polkadot as it stands, the relay chain. We use the Blake to hash scheme throughout in the protocol spec. We make use of the Ketchak 256 as well, but only in, I think, one place, the beefy sub-protocol. And that's basically just to allow it to easily provide easily verifiable proofs to chains that use the Ketchak hashing scheme, not least Ethereum. When we're using hashes, I subscript with a length if I only want to take the first few bytes of the hash. Yeah. We have our serialization codec or encoder, calligraphic E. This is defined fully in the appendix. And if we need to decode, we have the inverse E inverse. Yeah, there's a bunch of stuff to talk about with the encoder, but I think I'll leave that. I don't think I need to describe it particularly here. Okay. There are a number of different sub-encoders. For example, E subscript 4 encodes into 4 bytes. And basically it takes a natural number and turns it into 4 bytes. In general, the encoding is little endian. If you're familiar at all, it's similar to how Polkadot encodes. It's actually very similar to how data structures are encoded in a C-like way, like C language-like way. And it's not exactly compatible with it, but big swathes of the encoding and decoding function are compatible with it. Yeah, I think that's relatively well explained in the paper. Okay, so signing schemes. Now we have a few different signing schemes that we use in JAM. We don't use the SR25519 signing scheme that is used by Polkadot. Instead, we just use the regular ED25519 signatures for most of the stuff that doesn't need anything special. We then have BLS, which is the same BLS that we use in Polkadot 1. And we have a new signing scheme, Bandersnatch, and the Bandersnatch ring VRF. Bandersnatch ring VRF allows for anonymized signing. Basically, you can sign as an unknown member of a known set. Yeah. So you might have a set with 100 members or 1,000 members. Well, you can say, I'm signing based on this context, and this is my alias. So you have a known alias specific to a particular signing context. And that alias identifies you for that signing context only. And it's not, it's not correspondent, like it's not, you can't work out, given an alias, what the public key is for the key that's signed to create that alias. They're not linkable. Yeah. This is very useful when we do our underlying consensus algorithm, Safrole, as it allows validators to anonymously claim tickets for block production. I'll get onto that probably not today, actually, but that will be in the next lecture. Since we work with anonymized sets, we need some way of identifying a particular set, and we do so with a ring root. It's quite a large blob. And we can turn a sequence of public keys into a ring root through this root function, calligraphic R. So we're able to basically take some identities and work out what the root is for those identities. It's very helpful if we are to get a VRF output, which is basically this alias that I mentioned earlier. So we might have a context in which we make a signature to prove that we are a member of a set, or if we're using regular Bandersnatch to prove that we hold a secret key whose counterpart is a particular public key. Given that, it can be very helpful to have some verifiably random quantity that you as the signer have no control over. VRF, the verifiably random function. And Bandersnatch can be utilized for this. In essence, you can pull out a 32-byte quantity that is, to all intents and purposes, random. It's not obviously random in the sense of cannot be predicted by anybody until some natural phenomena happens. But it's random in the sense that the discoverer has no ability to bias it. They can either provide it or they can keep it away, but they can't change it.